Today we're going to take a look at a little bit of set theory. So we'll get through about half of this section today. So most of what we're going to look at here at the beginning, as with most sections of material, is a lot of vocabulary. So make sure that we're on the same page in terms of describing things. So first of all, a set. So a set is simply any collection of objects. The collection could be people, so it doesn't have to be things. The collection could be something virtual, right? Like the songs in your playlist, all right? But it could be actually physical too, like the books on your bookshelf. Elements are the individual objects in a set. So if we're talking about the people, maybe we're talking about this group of people, you would each be an element of this group, Math 1203A. If we were talking about the songs on your playlist, it would be the individual song that you would be listening to right now, or something like that. And if we were talking about the books on their bookshelf, it would be an individual book pulled off your bookshelf. Those would be the elements in those sets. There's a couple different ways that you can describe sets. One is called the listing or the roster method. I'm just going to give you an example of one of them. So the listing or the roster method might be something like this, where it lists specific numbers. You could list all, like if I looked at the roster, right, for this class, it lists all y'all's names. So it's just a listing of whatever you're describing. Generally, in most resources, you have to actually list them out. Sometimes what you'll see is something where, this is not a very exciting one, bear with me, but pretend for a moment, where they put ... somewhere and they don't actually list a portion of it. Your book tends to go with that being still called a listing method, where it's indicating what the list would normally be. Okay, so I'm just trying to give you an example that matches, not that this makes any sense to write as the ... between 7 and 9. Okay, it doesn't make any sense. But if I talked about something like this, you would all be like, well, yeah, I can't list them all out forever, right? And the ... makes more sense in that context. There's also a notation called set builder notation. Set builder notation is, so this is an example, not that they all are exactly that one, of course. Set builder notation is a notation that encompasses a way of describing without listing everything out. Sometimes it's simply not possible to list everything out. For example, I could list all the whole numbers, 7, 8, 9, that's fine, but I can't list all the numbers between 7 and 9. Like, it's not even possible. I have to have a 7.1 and a 7.01 and a 7.3 repeating. Like, there's no way to physically do that. So we have to have other methods as well, especially when you have resources that don't kind of, allow for this ... business to encompass what's missing between. So the next method, the set builder notation method, is the generalized way that this is done. So it starts out with curly brace, just like the other one. And it uses some variable. It doesn't have to be X. You can be more creative if you wish. I had a student one time who always liked to use the initials whenever she was doing things, initials of her friends. So she used a lot of J's and L's. I don't know. It's just what she used. Then you're going to put a bar. I'll tell you what all this means in a second, but you're going to put an X, you're going to put a bar, or a variable in a bar. And then you're going to describe these items that are listed, because I'm just going to try and do the same example. Well, these are the items between 7 and 9. Okay, so 7 is less than or equal to X is less than or equal to 9. Could do that, right? But I need to make sure that I'm only including 7, 8, and 9, right? I don't want to include 7.5 if I'm trying to describe that same set. So I need to tell it something else, like X is a natural number. We're going to have another notation for that very shortly. But it's a natural number. So natural numbers, which is what we're going to start with in a moment on the next slide, are sometimes also called counting numbers. They're the numbers that you first learn to count with. So when you first hear a child count, they start with the number 1. And then they go to 2, and then 3. So those are considered our natural numbers, or they're sometimes called counting numbers. So our first symbol that we're going to talk about is that N. So it's always written with 2 lines on the left to distinguish it from just any old N. And these are our natural numbers. They are the ones you naturally learn to count with. So 1, 2, 3, ... So my example on the slide before, they were natural numbers, 7, 8, 9. Those would be in the list that you count. They're natural numbers. Along the way of learning numbers, you have to sort of add in more stuff, right? So people start asking questions like, you're learning to add and subtract and multiply and divide, and then somebody says, okay, well, what if you have 3 apples and you take 3 apples away and you're left with, well, you need something else that's not in the numbers 1 through 1 and up. You need something else. You need a 0. So the next numbers are actually called the whole numbers, and they're not that much different than the natural numbers. They include everything that I've included already, and they include 0. So it's a very uninteresting addition, but necessary. I need the number 0. Agreed? I mean, we do. We got to have a way of describing, and 0 is a helpful number to do that. And then there's that kid on the bus trying to torment the little first grader and says, well, but you can do 5 minus 3, but what happens when you do 3 minus 5? Well, all of a sudden you don't have enough numbers, right? You need a number to represent what happens when you take 3 minus 5. So if you sort of expand your number system a little bit further, you have what are called the integers. Now, notice integers is not I, it's actually Z. It's actually coming from the Greek word for integers. We don't use the I think primarily because we would have to remember that it's integers versus irrational. We have another I word that has, connotation in mathematics. So we go with the Greek letter Z. So N for natural, W for whole, Z for integers. And the integers kind of have this ... on both ends because you have to go both directions from 0. Now notice it doesn't include just the negatives, it's positives too. So I'm building upon my world, right? I'm not taking things away. I'm building on pieces that I already have. Previously, I had only positives, and then I had positives and 0. Now I have the positives, negatives, and 0. And in fact, these are the only 3 number systems that we're even going to work with in number theory. This takes us through chapter 5 of our book. Whole numbers, integers. That's it. Those of you who've had proportional and statistical reasoning and or geometry and measurement, you've encountered some others. In particular, in proportional and statistical reasoning, we encounter one that we designate with the letter Q. We didn't talk about it as being the letter Q in Prop and Stat. Some of you are like, wait a minute, I don't remember that. We didn't use the letter Q when we talked about it, but these are called the rational numbers. Rational numbers do not have a way for us to write them out like we just did. I can't even remotely put these ... lists. It doesn't make any sense. So instead, I'm going to give you a verbal description of what they are. These are any number that can be written as a ratio. Ratio, that means fraction, if you haven't heard that word in a while. So it actually includes all the numbers on the screen already. It includes the number 3, because 3 can be written as a ratio of 3 over 1. Same thing for negatives, right? I can just write, negative 3 over 1. Those are ratio representations. I can do it with 0 as well. 0 over 1 if you wish. 0 over 5 if you wish. If I can write it as a ratio, it's a rational number, so all of these count. But what this expands our worldview into is you also get things, these are some of the new numbers you get, like 1/2 and 0.4. And you even get things that repeat, like 0.7 repeating would be in this list. Yeah, we're not doing that in this class, but those are all considered rational numbers. And the reason is because I can write them each as a ratio. And I'm not going to, sort of belabor the point too much, but 1/2 is already written as a ratio. 4/10, 0.4 is 4/10. And if you've had proportional and statistical, you might remember that 0.7 repeating is actually 7/9. So they have a way to be changed into a ratio, which is what makes them rational numbers. So we have natural numbers, we have whole numbers, we have integers, we have rational numbers, and the last one that we're going to discuss for right now are our reals. So our real numbers, I didn't mention it. Obviously you see that we've got rational and we've got real, and those both start with the letter R. Real numbers gets the R as its notation. The reason that we use the Q here is not based on Greek. It's actually based on the word quotient. A ratio is a quotient. Quotient means division. You're dividing something. So that's where that Q is coming from, is the word quotient. Real numbers, again, we're broadening our view, include everything listed here. But they also include something that's not listed here that is distinctly different. So the real numbers include both rational, that's everything above, and irrational. And we won't talk specifically about irrational numbers except to say that you've seen them before. So some examples of irrational numbers would include pi. You most certainly saw that if you've taken geometry anywhere along the way. Pi is involved. You've also seen things like a square root of 2. That's an irrational number. Another one that you may or may not have seen is the number e. That just depends on the math that you've had, probably in high school. So these are some examples of irrational numbers. And the reason they're irrational is because they don't have any way to write them as a ratio. You might remember that the number pi can be written as 22/7, but that's an approximation for pi still, just like 3.14 is. They're not exact representations. They're just approximations. So those are considered irrational numbers. So if you combine the irrationals with the rationals that we already have, you have the real number system. The only type of number that we're not discussing, period, ever in any of these math courses are what are called imaginary numbers. Again, you might have seen them along the way. The imaginary unit is the square root of -1. It's usually taught in college algebra here on campus, an algebra 2, or maybe a pre-calc class in high school, depending on what you've had. So those are considered imaginary, not because they don't exist, but because that's the name somebody gave them. Okay? So there's one more thing that we need in terms of symbols. The thing that we need is we need the symbol that looks like kind of like a C or kind of a curve, and it's got a line through it. Okay? So it looks a little bit like an E once I put the line through it. And we need the same symbol with this line through it like this. The first one means is an element of. So I mentioned on our very first slide the word element. Element just means the individual items in a set. So, right, each of you are elements of this set, Math 1203A. So if I were to put your name and I were to put that E symbol that I just wrote down, and I wrote Math 1203A, that would be a true statement, So Caleb is an element of Math 1203A. What do you think it means when you put a slash through it? It is not an element of, just like with a not equal sign. So far, so good? Okay, so using these, we're actually going to take a step back and we're going to write this set builder notation a little better now. So right over here, I had to write out this long descriptive phrase, and I mean, it's not super long, but it's pretty wordy. X is a natural number. And what I'm going to do is I'm actually going to write it with symbols now. So with symbols, we would say X is an element of N. And it compacts it. And it means the same thing. So what this actually says now, reading it from left to right, is this is all X. That vertical bar is read as the words such that 7 is less than or equal to X is less than or equal to 9, and X is a natural number. Okay? So we're going to practice that for another example over here. We're going to write the set of all natural numbers less than 5 using, first, the listing or the roster method. So the listing or the roster method is when we actually write them all out. So what number, if I'm sort of going from smallest to largest, is my smallest natural number in this set? Because it is natural numbers. 1. And then what? 2. And?
3.
Do we get to use 4?
No.
Yeah? Do we get to use 5?
No.
No. Because it says less than, right? So we don't get to include 5. Common mistake, sometimes people want to throw 0 in. Remember, 0 is a whole number, but it's not a natural number, and this one said natural. So that would be the listing or the roster method. If I'm doing set builder notation, it always starts the same way, curly brace X bar. And I have to have both descriptions in here, the fact that I circled less than 5 and the fact that it's natural numbers. And it really doesn't matter what order you put them in. So if you wanted to do the natural numbers first, you can. This is X is an element of the natural numbers. It's got to be in there somewhere. I'll just go in order from left to right in terms of the problem itself. And then I need to write in symbols, X is less than 5. So with an inequality, I can write X less than 5. Okay, what do you think? Okay, so far? Okay, so let's talk about when two sets are equal. As you might imagine, two sets are equal when they contain exactly the same elements. Okay, now there may be more than one way to describe them, right? Like, I could describe Dr. Hand's kids, and my husband could describe Pastor Jeff's kids. And we're talking about the same group of kids. So it's the same set, even though we've described it differently. Does that make sense? Over here, we can use the descriptive phrase, or we can use this where I wrote down X is less than 5. I could also write X is less than or equal to 4, and everything else be the same, and it would actually work. That's the same numbers, right? So it's another way of writing it, but the sets are equal. A one-to-one correspondence is a pairing of elements between two sets, such that each element of one set is paired with exactly one element of another set. So, sort of visually speaking, what has to happen is you have to have the same number of things. So, for example, when I was a child, my mom had a friend, and my mom's friend had 3 children, and my mom had 3 children. And so when they took all 6 of us out, it looked like, a little bit of a circus. But we had myself, I'm just going to use initials, K for Krista. My sister's name's Ginger. My brother's name's Chris. So there were 3 of us. And then our friends, their names were Christina and Amber and Megan. And because there's a one-to-one correspondence, that's a pretty good environment in which to have friendships, because everybody's got a buddy, right? Nobody's got to share. Kids don't share very well. Did you know that? Yeah, I hope you know that. So you can make this sort of pairing, and it doesn't even mean that they always have to be paired this way, but you can make a pairing between the 2 groups, 1-to-1. No sharing needed. So when you have the ability to do that with any 2 sets, groups of items, right? So any 2 sets for which there exists a one-to-one correspondence, they have to have the same number of elements, right? This is the problem when you don't have the same number of people, is that you have to do some sort of a sharing to make it work. So when you have the ability to have the same number but not the same items, we call it equivalent sets. They're equivalent. This is one of those unfortunate phrases because when we use it in regular English, equivalent and equal mean the same thing, right? When we're using it in set theory, they don't. Equal means exactly the same, but equivalent just means the same number of things. Now, while it's valuable for me to have said, hey, look, there's 3 kids, and then you've got 3 kids, and we can, get together, and they can all have a buddy, and nobody has to be sad because they have to share. Like I said, it didn't actually always work out that they were roughly the same age as we were as well. It didn't always work out that I played with the oldest, and my sister played with the middle one, and my brother played with the youngest. That's not how it always worked out. And so sometimes it would work out differently depending on what we were doing or what you were wanting to do, right? So as we're taking a look at number 2, the question becomes, well, how many different ways could you have done that then? How many correspondences could we have made? So this question doesn't ask specifically about my 3 people and 3 people. It asks about a collection of 6. Okay? So imagine that you have 6 people in this set. All right? 6 people over here and 6 people over here. So I'm going to change analogies for you now, and we're going to imagine that we're doing like a dating game. Okay? There's 6 ladies in the room, right? 6 ladies in here, and there's 6 gentlemen out in the hallway. Okay? And gentleman number 1 comes in, and how many different people could he be paired up with? 6, right? Okay? So gentleman 1, I'm going to just write this down. This is gentleman 1. And he had 6 different options. But once the 2 of them pair up and they leave to go on their date, and number 2 comes in, how many options does he have?
5.
There's only 5 people left, right? So there's only 5 people left for him to choose from or be paired up with. Well, then what happens? Then there's 4 for the next one. And right on down the line, right? Whoops. So we have 3, we have 2, and then by the time the last gentleman walks in, there's 1 woman left in the room waiting. They have a matched up pair. There's only 1 choice left. But what happens is that we can actually multiply these number of different options together to find the total number of ways that any pairings could have happened. So grab a calculator if you'd like. We've got 6 times 5 times 4 times 3 times 2 times 1. What does that give us? Actually, let me put it down here. 720. Is it any wonder that dating is so hard? There's lots of choices, right? I mean, but realistically, there are. I mean, and that's just 6 people. Just 6 people, and there's 720 different ways that you can correspond 6 men with 6 women. Okay? In a randomized way, anyway. All right. A little bit more vocabulary. Cardinal number. Cardinal number simply means the number of elements in a set. And it's written, if our set is written S, then the cardinal number is written in parenthesis S, close parenthesis. Okay, so like if we're looking at this class as a set, I can count you all, and that would be our cardinality, right? If you're looking at your playlist on the phone, right, you could count the songs. Okay, that would be the cardinality. So it's just the number of items. A set is considered finite when the cardinal number is a whole number. Right? All the sets that I've described so far, with some exceptions of some of the number sets, are actually finite sets, right? The playlist on your phone, the books on your bookshelf, the people in the class, those are all finite sets. Many of the number examples I've described are infinite sets, a set for which the cardinal numbers is not a whole number. And of course, they're infinite because they continue on with that ... at the end forever. So all the numbers I wrote over here, these different sets of numbers, are all infinite. Natural numbers, integers, Notice it's interesting because the whole numbers and the natural numbers have a starting place, right? They have a place where they start, but they are infinite on the right-hand side, and some of them are infinite on both directions. And then you have rational numbers, and they're even infinite between any two numbers, right? There's an infinite number of rational numbers between 0 and 1. It's infinite. Can't count it. Oops. And then the last one, perhaps the most fun, is the empty or the null set. So this is a set that contains no elements. It has a cardinality of 0 because it contains no elements. And it has two ways that you can write it. You can write it as a 0 with a slash through it. So if you are one of those people who likes to write your zeros with slashes through them already, you have to stop that now. Right? This has a meaning outside of it just being a 0 in maybe your normal writing. Okay, your 0 and this 0 with a slash through it have to look different. Another way you can write it is to have the curly braces with simply nothing in them. The 0 with the line through it's more common. Okay. So null set, what is it? Well, we're going to actually skip to the very back of your packet. And you're going to write one for me after I give you an example of mine. Example number 11, although I probably should just change the order of things, but I like to do it here. Asks you to create a real-life example of the null set in your life. So, I'll do mine. By the way, it's worth noting that my example used to be the teenagers in my house, which is not a null set anymore in my life. So, instead, we're going to do the infants. And Dr. Hand's house. That's a null set. It describes something for which there are 0 of. There's 0 infants in my house. So, I want you to take a minute, and I want you to put some curly braces and describe, and you can't use the word number of in it, right? The number of part of it is simply what is going to be the 0. So it's the description part without that phrase, right? This is the infants in my home, not the number of infants in my home. That's the cardinality. So write a description of something that is true for your life, for which the cardinality is 0, or it's a null set. I'm going to take a volunteer. Who's willing to tell us what your null set says? Somebody be bold. You don't want me to volunteer you. The longer we wait, the less time you have to do group work.
The animals in your house.
Animals in your house. Perfect. Somebody tell me something.
Money in my bank account.
Money in my bank account. You know what? That often has an example given. Good job. Thank you, Haley. Money in my bank account. I'm so sorry, by the way. That's sad.
I put the sisters I had growing up.
Sisters you had growing up. Very nice. My mom was an only child, so she had no siblings growing up. Yeah. Hey, anybody else want to do one real quick?
Brain cells I have left.
Brain cells you have left. Oh, that is highly unfortunate. I'm so sorry. So I'm going to give an example that's on somebody's page, but nobody wants to read it, as I always have somebody in my class say, my boyfriends. That's what I always have somebody say. Nobody wants to say it out loud today. That's okay. We appreciate it anyway. All right, we're going to do just a couple more examples, and then we'll go back to our homework or to our group work. This one, we're going to look at example 3. It's got 4 parts to it. All right, so our goal on this problem is to find the cardinality. So again, cardinality means the number of items in a set. Okay, so this is a counting game. We're just counting things. So you've learned a little bit of how to count things like A and B because we did Gauss's stuff, right? So we'll practice some notation too. This is the number of items in set A, so it looks like that. That's the notation for it. How many numbers are there from 9 to 99, whole numbers? 90, you're close.
91.
91. So how do we get 91?
You subtract 98 or 99 minus 8. You do
Yeah.
that before 9.
Yeah, so we subtract the one before 9. You guys remember that? Yeah, so 99 minus my 8, so this is actually 91. How about the number of items in B? 1,000? We're close. Should be 1001. Yeah?
Yeah.
Okay, so subtraction-wise, again, it's the number at the back minus the number that comes before. So what comes before 2?
0.
0, actually, in this sequence. So remember, we got to stay in the sequence. These are even numbers. So we would have the number 2002 minus 0. But then these are only numbers that are even. So it's half of them. Or you could say they're skip counting by 2s. So 2002 divided by 2 is 1001. C looks a little bit funny, but it isn't nearly as hard as it looks. The reason C looks funny is because of this stuff here at the beginning. So what I would like to do first is to show you what this is describing, and then we can talk about the fact that it kind of doesn't matter what it's describing on the counting question. This is saying that I'm going to take each one of these numbers, and I'm going to write the square of it. So I really have 1 squared, 3 squared, 5 squared, all the way up to 99 squared. Does squaring them change how many of them there are? No, not in the least. So counting these is equivalent to counting these, right? So I really just need to know how many numbers I have from 1 to 99. Does anybody know what that is?
50.
It is 50. Marissa, how did you get 50?
I did 99 and then I minus negative 1 because it's the one before and the set for 1 and then I divided by 2.
Great. So the number that comes before 1 here would actually be a negative 1, because again, we're doing just odds in this sequence. So I have 99 minus negative 1, which is the same thing as addition. So then 99 plus 1 would be 100 divided by 2. That's not the only way, that's 50, not the only way you can do it. You can also recognize, hey, this is really like all the numbers from 1 to 100, and then it's just the odds. Well, 1 to 100 is 100 numbers. It's half of them. That's why it's 50 instead of all 99 of them. D is interesting. D says that it wants all the numbers x, where x is equal to x plus 1. It has to be natural numbers to make this work. The description itself says natural numbers. So I need numbers so that when you add 1 to them, they're equal to themselves. What's a number that's in my set? Let's think through some numbers together. Is 1 in my set? If I take the number 1, is this a true statement? No.
0.
Let's see if 0 is in my set.
But it's natural numbers.
Yes. Oh, that's true. It is natural numbers, so we shouldn't have tried 0. But does 0 work? It doesn't, actually. But you're right. We should have tried natural numbers only. I apologize. Let's try 5.
Is it a null set?
It is a null set. Yes, indeed. There are no numbers that do this, right? You can't take something, add one to it, and leave it unchanged. Not within the sets of numbers that we've discussed. So this is actually equal to the null set. Now that's not the question that's being asked, but it is the null set. The question that's being asked is what are the number of items in it? And that answer is 0. So if you answer null set, I'm going to take some points off because that's not the answer to this question. It is the null set, but the question is how many items, right? What's the cardinality? Any questions on any of those 4? Okay, we're going to push pause there and we'll pick up there on Friday.